So in this example, this is 5.9. It's based on the example we just did a few minutes ago. There should be a question mark there, right? 5.2.2. But you should be able to find that. It says, what is the acceleration of the front of the wheel in that example? So in this example, there's a wheel rolling around with constant velocity rolling in a circle. And so the wheel's rolling with velocity v0 and around a circle of radius rho, where the radius of the wheel is b. And so we pick up a coordinate system that's just going around attached to the center of the wheel, but not rotating with the wheel. It's just going around, and so its x-axis points inward, its z-axis always points up, and its y-axis points backward from the direction the wheel is going, like this. And so it just kind of goes around like this. So just like in the previous problem, I've just shortened it up a little bit. I have to write out all the acceleration terms, right? This is the acceleration of whatever point I'm interested in the prime frame. This is the transverse acceleration. This is the Coriolis acceleration. This is the centripetal acceleration. And this is the relative acceleration of the frames. And again, in this problem, because I've picked a frame that's not coaxial, it doesn't have the same center, then this frame is accelerating relative to this one with a centripetal acceleration because it's going in a circle around my inertial frame. And so if I'm looking at the point on the front of the wheel, right, that's what the problem is. What's the acceleration of the front of the wheel in this example? The acceleration of that point, this point, is just going around the center with a speed v0. And so its acceleration in the prime frame is just v0 squared over b. It's a centripetal acceleration. And when it's here, the acceleration is, sort of along the j-hat direction. So that's that. And so I'm just going to work through these guys. This guy is 0. Omega dot is 0 because it's traveling at a constant velocity. If I want to evaluate the Coriolis acceleration, I have to evaluate omega, which is just v0 over rho. It's just the velocity of the wheel around the circle divided by the radius of the circle. And since it's going this way, it's in the k-hat direction. So that takes care of this guy. And then v prime is the velocity of the point of interest on the wheel. And since it's rolling this way, it's in the downward direction, right? And so it's minus v0 k-hat prime. Its position is minus b j-hat prime, because here's the 0 axis, here's the origin, and the y-axis points this way, and it's that way. So it's minus b j-hat prime. And then the acceleration of this frame relative to this frame is just a centripetal acceleration, v0 squared over rho. And the acceleration of the frame is towards the center because it's orbiting the center of the circle that is a radius of rho. And so now I can go back to these guys and I can write out all the terms. This is just a prime, it's just v0 squared, over b times j-hat prime, plus the Coriolis term 2 v0 over rho k-hat prime cross v, right? It's omega cross v, but v also points in the k-hat prime direction in the negative, but it doesn't matter. The cross product of k-hat and k-hat prime and k-hat prime is 0, so the Coriolis force goes away now. The centripetal term, which was 0 when we were looking at the top of the wheel, is no longer 0 because my omega cross r hat prime is now v0 over rho k hat prime, which is my omega, crossed into minus b j hat prime, which is my r. And when I work that cross product out for those three, so k hat cross minus j hat gives me an I hat, and then k hat cross I hat gives me a j hat. And so the direction I get out of this is j hat. And then if I work all those terms out, I get a v0 squared over rho squared times b. And so that's what that guy gives me. And then this is the relative acceleration of the two frames. So that's my answer.